Welcome everybody to the solutions to problem set number 9. Again, a bit on the lengthy side, I'm afraid. So in the first exercise we need to show that this here, the subgroup generated by the set M, can be written like that. And this monstrous set here I abbreviate with this symbol, M, in these brackets. So to show that these are the same, we first show that this here lies in this set, and then the other way around, and then they must be the same. Okay, we're following the hint. First of all, we show that this here, this set, is a subgroup of G, of course, by using the subgroup criterion in its condensed form. Obviously, this is not the empty set. Because M itself is not the empty set, I have at least one element in M, so I can take simply this element, x to the power of 1, which is an element of this set, so this is not the empty set. Okay, next we take two arbitrary elements of this set. By definition, they look like this. G can look like that, and H can look like that. M must not be equal to N. And the exponents, of course, can be different, either 1 or -1, but not in the same order. So I call those exponents here delta. Now we have to show that then again this product here of G times H inverse also lies in this set, and then we know that it is a subgroup. Okay, this here is G. Now what is the inverse of H? Remember the formula for the inverse. We turn around the order of the elements and take the inverses. So this here is yn, and here I take the negative exponent because then I have the inverse. It's either to the power of 1 or to the power of -1. If I take the negative of that, I clearly get the inverse. And now I take a look at this. This is exactly of this form. This is a product of elements of M, of length M plus N, which is a natural number, and all the exponents satisfy this condition here. So this clearly is, again, an element of this set, thus showing that M indeed is, M in these brackets, is a subgroup of G. And then we are done, because clearly M is a subset of this. Simply take here words of length 1 with the exponent 1, then you get all the elements of M. So M is a subset of this here, but this is a subgroup as we just showed. And then, because this here is the smallest subgroup, it must already be a subgroup of M. This was exactly the definition of what it means to be the smallest subgroup containing M. And this shows what we wanted to show. So here I do not need subgroup. Subset is enough, but it's also a subgroup, of course. Okay, now the other inclusion is pretty easy, because we know that this here is a subgroup of G. So it is closed under products and inverses. What do I do to get this set here? Well, I take all the products of elements and their inverses. But because this is a subgroup, all these expressions never leave M in pointy brackets. And that's it. Okay? I hope that's enough if I write it down like that. Being a subgroup means it is closed under putting two elements together that lie in here, which clearly is a subset of the smallest group containing M, yeah, and the inverses. And I do nothing else but putting those elements together or their inverses. And this means that all these words practically by definition lie inside of M. Okay, I just broke my promise. I promised this is a friendly introduction, so let's try to write it down a little bit better. So maybe like that. If xi is an element of M, which is clearly a subset of pointy brackets M, the smallest subgroup containing M, then xi to the epsilon I is an element. This is trivial if epsilon I is 1, but also if epsilon I is -1, because this as a subgroup is closed under inverses. And so this means this product xi to the epsilon I times xj to the epsilon j, again here by being closed under products, is an element of M. So all those words which have exactly this form, if I iterate it, lie in M. And this means that this whole set is a subset of this M here, the pointy bracket M. And I think that's good enough. Okay. Okay, exercise 2a. We are supposed to prove this commutation relation for the generators S and R. So that RS is a reflection is a fact. You could either check that by writing the permutations down explicitly and find out that this corresponds to reflection, or let's just assume that we already know that the rotations in Dn are exactly the powers of R, and that there are only reflections and rotations. This is logically a bit problematic because we use this stuff to prove that the Dn consists exactly of these elements here, but whatever. So we assume that this here is a rotation, then it follows by multiplying with the inverse of R from the left side that S is a power of R. So S would be a rotation, which obviously it is not because it's a reflection. Okay. So either way you can convince yourself that the product RS is a reflection, but this means that the square of RS is the identity, because reflections have order 2. So RS is the identity. We multiply both sides with R inverse from the left, then this R here cancels and we get this. And then we multiply by S from the right, because S squared is the identity, we end up with this result here. And this is pretty nice because we do not need the permutations or to check what both sides do to each vertex. This is simply using that RS is indeed a reflection. But as I've said, it's logically a bit problematic if we do not know this here yet. So anyway, the other way. So the second way is the geometric way or the permutation way. We use what these two symmetries actually do to the vertices. Remember, the rotation moves vertex I to vertex I plus 1, except for when I is n, then n gets moved to 1. I rotate the n-gon by 360 degrees divided by n. And our reflection moves vertex I to vertex n plus 1 minus I for all I between 1 and n. Remember, that's how we defined R and S. So let's see what SR does to I. This is S of R of I. So this is S of I plus 1. So this is n plus 1 minus I plus 1 in parentheses. So this is true for all I between 1 and n minus 1. And SR applied to n is S of R of n is S of 1, which simply gives me n. So this here is what SR does. Now R inverse S applied to I is R inverse of n plus 1 minus I. Now what does the inverse do? Of course it moves I to I minus 1, because the composition of those maps is the identity. Or geometrically, we just move the n-gon in the other direction. So we rotate by minus 360 degrees divided by n, or by n minus 1 times this angle, because we do not allow negative rotation, but the effect is the same. I gets mapped to I minus 1. So I end up with this expression here, minus 1, because I rotate in the other direction, or as I said, n minus 1 times the angle. So this leaves me with n minus 1. So they have the same effect, and R inverse S applied to n is R inverse applied to S of n. S of n is 1. And the inverse rotation moves 1 to vertex n. So here they also agree. So this proves, because they have the same effect on all the numbers of all the vertices from 1 to n, so these maps here must be the same. Of course, this is preferable because it's much shorter, but here you really use what R and S do, so maybe that's also a good exercise to think about that. Okay, exercise 2b. We are supposed to prove this general formula using induction on K. If you've never heard of that before, I'm doing it very slowly, though that hopefully you can follow. But you could also skip that and try the case n equals 6 for yourself and convince yourself, for example, that SR squared is the same as R to the minus 2S, and so on. I'm not going to do that here, but please write down the permutations or think about what R squared does and check some cases. So, okay, here we go. Let's review proofs by induction, or let's learn them for the first time. We have a statement that we are supposed to show for any natural number. That's always the setting in an induction proof. Here, the powers of R repeat themselves after k equals n, but that's not important. If we can show it that this holds for all natural numbers, then especially it holds for those k. And it doesn't matter that the powers repeat themselves. So, to do this, we first show the induction start, induction beginning, I don't know the correct English term. We show that S for statement, S1 is true. But we just did that. This was part A. We proved this here, that for k equals 1, this is true. This was quite some work. This was not trivial. Then, in the induction step, this is important, we assume that this statement here is true for some fixed number k. We do not say that we already know it's true or that we have proven that it's true. We simply assume that it is true. This is called the induction hypothesis, abbreviated with IH. And then we show, using this, that then also sk plus 1 is true. So the next statement for the next natural number. And if we can do this, we are done. Because, we will do this shortly, but let me explain the logic behind this proof. Now we have the inductive loop, induction loop, again, I'm not sure. We know that S1 is true. But then, by the inductive step, we know that S2 is true, because we have shown that if Sk holds, then Sk plus 1 also holds. Now, if S2 is true, then again by the inductive step, S3, 2 plus 1, is also true, and so on. And thus, by simply showing these two things here, we have proved this statement for all natural numbers. That's the beauty when you're using proof by induction. So let's do the inductive step. So we assume this here is true for some k. So this is the inductive hypothesis. And we want to show that then it's also true for k plus 1. This is pretty easy here, because s to the s times r to the k plus 1 is s times r to the k times r. This is always true. And now, by the inductive hypothesis, we can switch the order if we use the minus sign here. So this is r to the minus k times s times r. But then by our inductive beginning, induction start, SR is the same as r to the minus 1s. This is what we proved before. And now again by the power law, this is r to the minus k plus 1 in parentheses. Because r to the minus k minus 1 is exactly that. And this is what we wanted to prove. And now the induction loop or inductive loop tells us that this is actually true for every natural number. Bam! That is proved by induction. Very, very elegant. And this would be a nightmare to write down without induction. Yeah, you would have to write down what r to the k does to vertex number I. You have to use modulo n, and it's a catastrophe. So this here is very, very recommendable. And I hope, even if you never heard before of proofs by induction, this was understandable. Okay, in part C, we are supposed to fill in the missing details here to show that Dn actually can be written like that. Okay, this is not going to be too much fun. It's just tedious to write down. But it's a good exercise to work with those groups generated by a set. So by definition, the group generated by this two-element set of R and S consists of those guys here, finite products of xi being either I, R, or S, and the exponents being either plus 1 or minus 1. So, for example, one element of this group generated by R and S would be a so-called word that consists of this sequence. R times R to the minus 1 times S inverse times R times R times R. Now what this means is, this is not the definition of the group generated by these two elements, but here something already happened. So here is already a step missing. So for example here, I take all the R's that are neighbors to each other, and this would give me R to the 1, minus 1, minus 1, so R to the minus 1. This would give me S to the 0, and this would give me R to the third power. So by combining all the R's and the S's, I first of all end up with an expression like this here, and the exponents can be integers, as you see here. It could be R to the minus 1, or it could be S to the 0. So in this case, this here could be simplified to R squared. Okay? Another word could look like this. R to the third, S, R to the minus 4, S, R, and so on. And now we're using the commutation relation that we can switch the S's and the R's. So here, SR so this would give me R to the minus 1S. Okay, and so this here would be R to the third, S, R to the minus 5S. Now here again, I can use the commutation relation. I have R to the minus 5S, which is the same as S R to the 5. Yeah, I simply used this. And then here I have S squared, which is the identity, so this goes away, and this leaves me with R to the 8. And maybe there's an S left here or not, depending on how the word I started with looks, but this should make clear that by using the commutation relation several times, I can always end up with an expression like that. r to the k times s to the power of 0 or 1, because there are no other choices. And now here, for example, if I am in D6, this would reduce to r squared, because r to the 6th power is the identity. Therefore, it's enough if k runs through the numbers from 0 to n minus 1. Okay, I hope this was enough, because to write that down in general, that's not going to be fun. So I'm going to leave it at that. Okay, this was not a perfect proof, but I think the idea got clear, and it's just tedious to write down in general. Okay, and finally we need to show these claims here 1 to 3, so that in the end we have proven that the order of Dn is 2 times n. Alright, so let's assume we have an element z that lies in this intersection here and is not the identity. Then, because it lies in the intersection, it must be an element of X, which was the cyclic subgroup generated by R. So Z would be R to the K for some exponent between 1 and n minus 1. Not 0 and not n, because then we would have the identity. And if Z lies in the intersection, it lies in Y. Y is the subgroup generated by S, which only contains the identity in S itself. So this implies that Z must be S. So it would follow that R to the K for one of those Ks would be equal to S. This, of course, is a contradiction, because this here is a rotation and this is a reflection, and they are not the same. If this is not enough for you, then observe that R to the K of vertex 1 gives me K plus 1, because I rotate K times 360 degrees divided by n, whereas S of 1 is always n. Well, this might still be the case that these here are equal if k is n minus 1. So this would imply k is n minus 1. But then we have r to the n minus 1 of vertex 2. I move it n minus 1 times. Then vertex 2 exactly ends up at vertex 1. But S of 2, remember S is the reflection about this symmetry line here. So S of 2 is n minus 1, and this can not be 1, because we're in the case where n is greater than or equal to 3. So this really shows that those cannot be the same. But since this is a bit tedious, I think it's okay to say rotation is never a reflection, but maybe once you should do it like that. Okay, claim 2. This here is the unique representation of an element that lies in here. K and L always these numbers here. So let us assume that we have two representations of the same element. R to the K times S to the L equals R to the P times S to the Q. Then by multiplying with R to the minus P from the left, I end up with this here. R to the minus P times R to the K is the same as R to the K minus P. And here it cancels. Then I do this. Then I multiply from the right with S to the minus L. So I end up with this here. But this shows that we have found an element in this intersection, because remember, X was the cyclic group generated by R. This clearly is an element of X. And Y was the cyclic group generated by S. This clearly is an element of Y. And because we have the same element, it lies both in X and Y. But we just showed that only the identity lies in this intersection. So we know this. Now K and P are numbers between 0 and n minus 1. So the only possibility for this to be true is if this is 0, because it cannot be n or 2n or any other power that would give me the identity. And the same on the other side. Q minus L must be 0 because it cannot be 2. S squared would be the identity, but the exponents are only 0 or 1. So the only choice I have for them is to be 0. So, and this shows that these exponents here must have been the same. So this exactly means what we have here, that this representation is unique. I think this is easy enough to follow, but if you've never seen such kind of proof before, it's not so easy to come up with that by yourself. Okay, now we are done because the bijectivity of this map was already explained in the video of lesson 9. This is exactly when I have unique representation. This map here is injective because I can have two different powers of R or S being mapped to the same. This would contradict this uniqueness. And it's obviously also surjective because all the elements are of this form, all the elements of xy. So this clearly is a bijection, and the rest of the argument was already explained in the video. All right, so we finally showed with a bit of hand waving here that the order of Dn is 2 times n.